So, thank you. Thank you very much. It's a pleasure to take part of this school. I love the schools organized by ICTP-SAIFR, and Hilda knows very well. And yeah, it's a shame that Arkady couldn't make it, and okay, you have to confirm with me. And let me introduce myself. I'm Jesus Gómez Gardeñes. I work in the University of Zaragoza. Oh, sorry. University of Zaragoza, you know, we just have the 550 years birthday, so it's a very old university in Spain. It's one of the oldest in Spain. And well, I did my PhD in physics there, so I'm from Zaragoza originally, and then I moved to several places as a postdoc to Italy, Israel, and Tarragona. Then I start to be some kind of stable, stabilized in the Spanish system, working in Madrid, in the Rey Juan Carlos, and finally, I have a fellowship, which is the Ramón y Cajal Fellow. It's like a tenure track position in Spain, and then I came back to my original university, and nowadays I'm their full professor. So there I have this group, with this fancy name, Gotham Lab, which is the group of theoretical and applied modeling. And, well, we are a very small group. We are 3 senior people with Luis Mario Floria and Carlos Gómez Ambrosi, and then some predoc students like Francesca, Dirisante, Pablo Gallarta, Santiago Lamata, Hugo Perez, and Pablo Valgañón, who is just finishing the PhD, and he's going to defend in 1 month, okay? And what we do in this lab, well, what we explore is this, okay? This is the general topic of the lab. It is, we study. Ah, okay. My beautiful face. Come on. And thank you. And this is the topic that we deal with, which is the emergence of collective phenomena in large ensembles, so to say, of interacting units. And this large ensemble of interacting units can be many things, you know, many systems, many complex systems. Can be, for instance, social systems, and there, for instance, we explore cultural transmission and the spread of information, misinformation typically, or more refined models like those in evolutionary game dynamics, okay? So we study how we cooperate and how we build societies like the one we have nowadays, polarization as well. We also explore technological systems, and we have made several studies about jamming transition. This is something which is typically focused in statistical physics. A topic which is very important nowadays is that of epidemic dynamics, and we have devoted a lot of years exploring this kind of models, from simple models to meta-population models, in order to inform public health agencies. And finally, we have also a very important topic of the group is the study of synchronization dynamics, okay? And that's what I'm going to talk about, okay, in these days. So let's start now formally, and let me start by the very basic notions, okay? So the class today will be very fundamental. So most of you, I think all of you, know what we are going to show here. And also note that the colloquium will be today at 2, so this class will be only 1 hour in order to accommodate a larger space for lunch, because I think this is more essential than the Kuramoto dynamics for our life, okay? So let's start from the or the simplest dynamical system. We have a one-dimensional dynamical system. X is a real variable, only one function here, autonomous system, no noise, is deterministic, so, I mean, cannot be simpler, okay? And, okay, this is a system, an example, just an example. This is an example which is very nice, and Strogas put this example in the book, because this is a nonlinear system, okay? And you can integrate this equation. I mean, you can easily find the solution of this equation, okay? But the solution is ugly. I mean, and if I ask you, I am not going to write the solution, ask you about how the solution looks like, it's really strange that some student or professor knows what is going on in the system, even if having the analytical solution. What you typically do in a system like this is to try to study qualitatively the solutions you have in your system. And this is the idea of nonlinear dynamics. don't use quantitative, even if you have quantitative information, we prefer qualitative information because we can describe as a whole the system, okay? And we have to describe the phase portrait, which is the important thing. In this case, the phase portrait is very simple because we can just plot as a function of the variable the velocities, okay? So we have the velocities, some velocities positive here, negative here, etc. And for instance, we can ask about fixed point solutions, which are those solutions, those points in the line in which the derivative is 0, okay? And obviously, because we have the sinus function, we have that every pi, we have a fixed point solution, okay? We can also look at the velocities, and we can see that in those valleys, we have negative velocities, and in those hills, we have positive velocities. And with this notion, we can also say which points are stable and which points are unstable, okay? So, for instance, you see here that this point is unstable because if I move slightly here, then I will go right. And if I move slightly to the left, I will continue moving to the left. So I will depart from this solution. This solution is unstable. Instead, this point is stable because any little perturbation comes back, is dumped out, and come back to the original solution. Okay, so we have two kinds of fixed point solutions, stable and unstable. And you can also check, as you usually check, looking at the derivative here in one dimension, the Jacobian in higher dimensions, obviously, and tells you that if you have positive derivative around the fixed point, then you have unstable solution. If you have negative derivative around the fixed point solution, then you have a stable solution, okay? This is the very basic notion. Okay, in this class, we are going to focus on periodic systems, okay? Periodic systems, now we have, again, one variable, but the variable is an angle. And this means that it's 2 pi periodic, okay? So the restrictions for such a system are the same, with the exception that this point has to be exactly this point. So this imposes a restriction to the function f, the velocity, that is this function must be a 2 pi periodic function, okay? Obviously, sinus is a 2 pi periodic function, so we are in safe hands and safe grounds, and we can use this as a 2 pi periodic solution, okay? Any question? Crystal clear, right? Okay, so let's start. Okay, this is the menu for today. This is an appetizer, okay? Let's explore non-uniform oscillator, okay, which is the very very simple case. Then we make the starter with the synchronization of one dynamical system with an external stimulus, okay, which is totally fixed. Then we go to the main, which is the introduction of the synchronization dynamics, which is and in particular, the introduction to the Kuramoto model. So we will make a big jump from 2 variables to n variables, where n can be 1,000, so to say. And finally, we have a dessert that maybe we will leave it for tomorrow because of the restriction of the time, okay? Which is to solve again the Kuramoto model, but using another formulation, which is very, very useful, okay? And I want you to be aware about. Okay, so let's start with non-uniform oscillation. Let's start with this dynamical system. So we have that the derivative, the velocity of the angle is equal to omega. Omega is a real number and is fixed, okay? So it's just an oscillator which is pacing at a constant velocity, okay? So we have this plot for the velocity diagram. Is there any fixed point here? No, there is no fixed point solution, okay? And in fact, what is doing the oscillator is just to make an oscillation with a fixed frequency so that the period of the oscillation is 2 pi divided by this omega, which is the parameter of our equation, okay? Okay, let's perturb this oscillator, okay, this phase oscillator with constant frequency with a term, which is a nonlinear term, and is weighted by this A, okay? So A weights the perturbation, the nonlinearity of the model, okay? If A is very small, what we have is just a modulation of the original velocity. So in some parts here, we have that the oscillator paces a little bit faster, and in other parts here, for instance, you see that for these angles, the oscillator paces at a rhythm which is a little bit slower than the original frequency, okay? So we can tune the value of A, and in this case, nothing happens. I mean, no fixed points appear, okay? We can But obviously, the period is not anymore this quantity, okay? We can calculate, and we will calculate later. Okay, let's do A stronger. Nothing happens. The period is whatever, but there are no fixed points. And if I start increasing a little bit more A, what happens is that you reach a point in which now you have two fixed point solutions. And it's very simple to say that here you have negative derivative, so this is stable, and this is positive derivative, this is unstable, okay? So for these 2 points, one stable and unstable, we have a new phase portrait, okay? Because before we didn't have any fixed point, now we have two. The point in which we have seen emerge two fixed points is a bifurcation. Which kind of bifurcation we have here? No, okay. Ulrike told you that this is a saddle node bifurcation, okay? From scratch, you have no fixed points, and from scratch, 2 points appear, 2 different points appear. One stable and another unstable, okay? So this is the typical saddle node bifurcation. That happens when this intensity, this parameter, reaches exactly omega, okay? When this parameter is exactly omega, then we have this saddle node bifurcation, and the phase portrait has changed qualitatively, okay? From having continuous flow on the line or on the circle to have two fixed point solutions. In fact, let me show you what happened before and after the bifurcation. Before the bifurcation, you have the circle. This is your system, and what happened that it paces and it continues the flow around the circle. In some parts, it is slow. In some parts, it is fast, remember, because of the modulation. This is what happened just at the bifurcation. In the bifurcation, in the saddle node bifurcation, one single point, which is stable in one part and stable in the other, so it's half stable, appears. So if you have the system and you perturbate it, what happens is that it makes one excursion in the circle and then come back to the original point. And finally, after the bifurcation, okay, which happens when the intensity is larger than this omega here, what happens is that if you depart from the unstable fixed point solution, then you end up into the stable solution, either in one way or either in the other, okay? Nothing more. Okay, very good. We can analyze what happened in the curves to the bifurcation by looking what happened to the period. The period is defined by this integral, okay? And after changing the variable from the time to theta, and this is the Jacobian, we have to solve this equation, okay? And this equation is analytical, so you can solve it analytically, and the answer is this. So the period is equal to 2 pi divided by this expression, which is kind of effective frequency that depends on A. Notice that if A is equal to 0, so this perturbation is not here, then you have omega. You have the square root of the omega to the square, so it's omega, obviously. And what happened is that because this is a square root, this is defined, this is defined as long omega is larger than A, or if you want, as long as A is smaller than omega. So we can plot this omega. Obviously, we can normalize by the original frequency. So we have 1 here when A equal to 0 as a function of A, okay? And we have also normalized A by omega, which is the critical value where the bifurcation occurs. And as you see, the frequency start to decrease. And finally, at the bifurcation point, the frequency is equal to 0, okay? Nothing more, nothing less. And obviously, this point, this area corresponds to this part, and this area corresponds to the other part. Here, there is the oscillation, and here, there are no oscillation anymore because there are two fixed point solutions. Okay, when we approach the bifurcation point, okay, we can put this expression, and we have this convergence to the critical point, which is the typical expression, the typical with the exponent 1/2 that you expect in a saddle node bifurcation, okay? And also, as you approach this point, what happens is that there are some parts in your excursion, you are still here, in which the velocity is very, 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 very tiny, okay? So when you pass in this area, so in the very slow area, the system almost becomes frozen, okay? And you have here this bottleneck because apparently the system does not evolve because the velocity is so small and then departs again. That's why saddle node bifurcations are also known ghost bifurcations, because before they appear, you have some clue, okay? And the system starts to chill, okay, because of these extremely low velocities. Okay, let's go to the next level. Any question? No? Crystal clear. Okay, perfect. Let's go to the synchronization now with of a system with an external stimulus, okay? And the equation is this one. I need to represent this picture. Let's see, this is our system, our friend, this firefly, okay? This firefly is described by a phase angle, this theta, okay? So this is the equation for the evolution of the phase of the firefly. And this firefly is in contact, visual contact, so to say, with this tree, which is full of fireflies, okay? And they are already synchronized. This is the typical movie that you find in the internet when you put synchronization, okay? You have one, this, and the other, which are the metronomes that we will see later, okay? So the thing is that this interaction alters the phase of the firefly. There is some kind of interaction which is mediated again by this parameter A, which is the interaction of the bulk, okay, towards the firefly. We assume here that the firefly attempts to synchronize with the bulk, but, and this is important thing, we assume that the bulk remains totally unaltered, okay? For the bulk, the firefly is just a perturbation so negligible that this frequency of the bulk, this capital omega, remains totally unaltered, okay? So what we have is just a single equation because this phase, okay, is just obey this dynamical system that does not depend on little theta, okay? Okay, since we have these functions, these sinusoidal functions of the difference, we propose, okay, to consider this new variable, which is phi, which is the difference between the phase of the bulk minus the phase of our firefly, okay? And let's see how is the equation of this new variable. The new variable, obviously, the derivative is the derivative of the capital theta minus the derivative of little theta. This is automatically capital omega, and this is just this equation, so we can write it. That's all, okay? And this is the equation we have to solve, okay? Again, we have a lot of parameters. We have capital omega, we have omega, and we have A. Okay, so what we can do is to try to reduce the dimension, okay, and adimensionalize, and this is achieved by just dividing this equation by A, okay, so we remove A from here, we divide A here, and we put A times T as the new time, okay? So we have a new time, which is tau, which is A times the original time, and also what remains here, which is this difference divided by A, we call it omega tilde, okay? It's like a new omega. And this way, these equations, after this change of variable, of the adimensionalization, has this form, okay? The evolution of the phase difference is equal to this omega tilde minus the sinus of the variable, the phase difference. Did you observe any similarity? What we have seen any similar equation in this 20 minutes? The previous one, yes. It's exactly the same. Here, omega tilde plays the role of omega, and here A is equal to 1. So, since I know what happened here, which is when A is equal to omega, I have a saddle node bifurcation, I can totally say that when omega tilde is equal to 1, then I will have a saddle node bifurcation, okay? Okay, so let's explore the system, but I know the solution already because it's the same system as before, so there is no need, but let's do it, okay? Let's assume that we have already synchronized firefly, so this difference is equal to 0, and then what happens is that we have this velocity portrait, okay, with two fixed points, because this fixed point and this fixed point is the same. This is the stable fixed point. This is the unstable fixed point. What happened here is that the two systems are already synchronized, and that's all, okay? Let's increase omega tilde, okay? How we increase omega tilde? Okay, we can increase omega tilde by increasing the difference between these two omega, the natural omega of the firefly and the omega of the bulk, okay? If they are not equal, what happens is this. If the difference is not very large, in particular, if the difference is not as large as A, remember that the saddle node bifurcation will happen when this omega tilde is equal to 1, then what we have is these two fixed points, and this is a synchronized state in which we have phase locking, okay? So what we have is that there is a phase difference between the bulk and the firefly, but the frequency is the same, okay? So we have, and obviously we have two different solutions. And if we increase a little bit more omega, so this difference is larger than A, so this is larger than 1, what we have is a saddle node bifurcation in which we have lost these two solutions, okay? Okay. What does it mean that omega tilde increase? Okay, let's go to the physical terms. Imagine that we have omega, this is the natural frequency of the firefly. The A is also set, so we have this interval, omega minus A, omega plus A, and this is omega, capital omega, which is the frequency of the bulk. Okay, this corresponds to the original situation in which the two systems are already synchronized. If omega is not exactly equal to little omega, then we have the second scenario in which we have still omega less than 1. And if capital omega is larger than this quantity, here or here, and it's the same, obviously, then what happens is that we have lost the synchronization, and now the two systems are totally desynchronized, okay? How can I control if I want to recover synchronization? Okay, these two are fixed, okay, because omega, capital omega is the frequency of the bulk, little omega is the natural frequency of the firefly. I cannot alter it. So what we can do is to increase A. If I increase A, I will decrease the value of omega and try to recover the situation in which capital omega is less than 1. So what I do is to enlarge A, and what I'm doing is to enlarge the frequency, the range of frequency in which I have synchronization, okay? Very simple, right? Okay. So if I vary the coupling, which is here the important thing, between the firefly and the bulk, we can adjust the range of entrainment and we can recover the synchronized solution, okay? In the bifurcation diagram then is very simple. If you have here the possible frequencies of our little friend, and here the coupling between the friend and the bulk, let's suppose that the bulk is spacing at this capital omega. If omega is exactly equal to capital omega, then we have full synchronization, and for the rest of the system, we have this, okay? Here we have phase locking, and here we have incoherent solution. And obviously, the border between the synchronized solutions and the uncoherent solutions is made via a saddle node bifurcation. So if you have here your firefly, it has this omega here, then you know how much you need to couple these two systems in order to enter into the synchronization in the distribution region, okay? And this is the critical coupling. Okay. Any question? No? Okay, so we are now prepared to get rid of the oversimplification that we have made, assuming that the bulk is already synchronized, or better. Now we are going to tackle the question of how this bulk achieve full synchronization, okay? Okay, and this is the problem we want to tackle. How do thousands and thousands of fireflies or neurons in our brain get synchronized, okay? And this is the open problem. Okay, in order to do it, then we are going to tackle the Kuramoto model, okay? But obviously, the Kuramoto model is not a model for synchronization in the brain. This is a school in which we are going also to talk about brain dynamics, okay? Synchronization model in the Kuramoto model is an oversimplification itself. But it gives a lot of insights about how synchronization emerges, how synchronization show up, and in the case I'm interested in, how the structure of our complex system, how the structure of our brain, how the structure of our society influence the onset of synchronization. Remember what I have told. A, the coupling between the firefly and the bulk is critical, okay? If you know capital omega and you know omega, we can know how much we need to couple, how much value, strength I have to assign to A in order to achieve synchronization, okay? Now, the question is how much I have to wire my system in order to achieve synchronization. But this is something we will tackle tomorrow, okay? Let's continue then with our system. And now let's tackle a very simple problem in which we have two fireflies, okay? The thing is now, this firefly, as in the original problem, is altered by this one, but this one is also altered by this one, okay? So now there is a mutual influence between the two fireflies, okay? So what is measuring the influence that makes the 2/1A? So A measures how to influence one, while B, this parameter B that appear in the equations here, is measure the strength of interaction, or the strength of influence that one makes over two. Okay, so this we have. A and B can be totally different, okay? And it happens in reality. I can influence a lot of friends, and my friend influence less to me, or the other way around, okay? So in principle, A and B are different, and look that the equations are, again, similar to those we have explored until now. The two fireflies have a different natural frequency, omega 1 and omega 2. The coupling is a sinusoidal term that depends on the frequency, the phase of the other minus my phase, the phase of the other minus my phase, and here A and B, which are the interaction strength, okay? Okay, so let's see what happened. We can represent, obviously, the system because these are phase variable in the circle. This will be the state of the firefly 1, the firefly 2. And as you see, the equation is demanding, is asking for a change of variable, okay? Because we have here and here the phase difference, okay? With different signs, obviously. So we are going to work with this new variable, which is the difference between the phase, the phase of the firefly 1 minus the phase of the firefly 2. And this way, we have this equation, which is just the difference between these two equations, okay? So you make the difference between these two equations, and you arrive to this one, okay? You see, omega 1 minus omega 2. And here, we adopt sinus of phi. So this is theta 1 minus theta 2. This is already here. And here you have to change the signs because you have theta 2 minus theta 1. So you have minus here. So both have a minus, so A plus B. Okay? This is the new equation. The new equation for analyzing this system. Okay? Again, does anyone remember this equation? It's the same. Again, it's the very same equation we just analyzed at the beginning of the class. Now, omega is this difference, and A is this sum. What we know here, when A is equal to omega, a sudden no bifurcation occurs. If A is larger than omega, we have phase locking, we have fixed points. If A is less than omega, we don't have fixed points. Now, if A plus B is equal to this phase, this frequency difference, we will have a saddle node bifurcation. If A plus B is larger than this phase difference, we will have two fixed point solutions. If A plus B is less than this, no fixed point solutions appear. Okay? We have solved it again because it's again the very same equation. Okay, let's do it. And the thing now is that the fixed point solutions, okay, these two fixed point solutions that happen when this is much larger than this, okay, this, are not real fixed points, okay? Because a fixed point solution here means that the derivative is equal, the derivative of the phase difference, of this phase difference is equal to 0. But this means that they are moving and that the velocity is the same. So it's a fixed point in this phi variable, but it's a dynamical solution in the original variables, okay? And this is very important. Okay, so let's assume there is a fixed point solution, so this part is equal to this part. This is what happened here. So I can have the solution, the precise value of phi, okay? This and this. Obviously, the sinus have two solutions, two angles satisfy this condition. And this condition, as I say, imply that the two fireflies move at the very same frequency, at the very same velocity. Okay, which velocity? Which is the frequency, okay, of consensus? Okay, let's go to any of these equations. Let's go to this one, for instance, and then you just put the solution of this. This is the sinus of phi. So you substitute this sinus by this expression, and then what you obtain is this expression. Okay? This is the frequency, the compromise frequency. And as you see, it's a weighted average. If A and B would be the same, this would be just the average. It would be omega 1 plus omega 2 divided by 2. But in principle, A and B are not the same, so it's a weighted average that if you represent it in the line, you will see that it's closer to omega 2, okay, here, because A, in the case, A is larger. So when A, which is the influence of 2 over 1, is larger than B, the compromise frequency will be closer to omega 2, and the other way around. If B is larger than A, this means that the influence of 1 over 2 is larger than 2 over 1, and the compromise frequency will be closer to omega 1. Okay? Yes? Okay. And this is the dynamical solution. As I say, these are fixed points in phi, but they are not fixed points in theta 2 and theta 1, but they are these solutions here, the flow in the phase plane, in which you see that they move a constant velocity. And you have these two solutions. You won't see this one because it's the unstable. You will always see this one, which is the stable one. Okay? Okay. What happens if the difference between these frequencies start to increase? We know it already, because we know that a bifurcation occurs when this is equal to this. So when this value reaches this one, then a bifurcation occurs, and these 2 points disappear as a saddle node bifurcation again, okay? Okay. We have explored this case. What happens if we have this case? Okay, so now we make the big jump, okay? The big jump, which is just to study the Kuramoto model, okay? The Kuramoto model, which is due to Yoshiki Kuramoto, which still is emeritus professor at Kyoto University, I guess, and supposed to pass from one-dimensional or two-dimensional flows to n-dimensional dynamics, okay? So this is a very big jump. And if you know a little bit about dynamical systems, when we pass to 1 dimension to 2 dimensions, it's okay. But when we go beyond 2 dimensions, a lot of things happen. Chaos, for instance, okay? So we are doing a lot of change in this jump. Okay, let's see what we can do. Okay, the Kuramoto model then is a collection of fireflies, so to say. Each one is defined by a phase, theta 1, theta 2, theta 3, theta n. And we assume that each firefly, each phase oscillator has its own natural frequency. Okay, so in principle, they are totally different. Okay? And these frequencies are randomly assigned, because remember, we have n oscillator, with n being very, very large, from a frequency distribution, which will be g omega, which has to satisfy, which is an unimodal function, and symmetric around the mean, okay? So for instance, a Lorentzian, a Gaussian, a constant, a step function, I mean, you need to be unimodal and symmetric around the mean. The mean frequency is conserved, okay? So if we have a mean frequency, no matter what happened with the system, the mean frequency will be always the same, okay? And because of this, it's typical to choose that the mean frequency is equal to 0. So that g omega is a function, okay, which is centered around 0, with positive and negative frequencies, and it's an even function, okay? Okay, these are the dynamics of the phase oscillators when they are isolated. By isolated is obviously not the interesting case. We have to put the interaction, and in the original Kuramoto model, what happened is that the interaction happens all to all. Okay, so we have that each oscillator sees n minus 1 other oscillators with different natural frequencies. And how is the interaction term? Okay, there is no other Homer Simpson now, but it will be similar to the equations we have studied so far. We have a coupling, which this K plays the role of A, okay, of our A. N is just a matter of normalization, because otherwise this coupling would diverge, okay? And we have the sum across all the nodes of the sinus of the difference of each node with me, okay? Because I'm I, okay? So this is the coupling, and nonlinear coupling is the sum of sinusoidal functions, okay? Any question about this? No? Okay, so this is our control parameter, okay? This is what we are going to control. Remember, A was the thing I could control in order to get into the synchronization area or getting out of it. And now K will be our synchronization control. So we can pass from a circle in which each oscillator paces at its own rhythm, and by increasing K, we can go to this solution in which the bulk, in which our fireflies are totally synchronized, and they all pace at the very same rhythm, okay? Yes? Okay, now I put the other example. I don't know if I have... You hear? Okay. Sorry. At the beginning, you see, I put that again. These metronomes start to pace and they have a different angle, okay? Maybe they have the same frequency, can happen, but the frequency obviously is not the same because there is some mismatch. And what happened is that they are coupled with this boot bar that move because you have placed here empty cans, okay? And these empty cans, empty, should be empty because otherwise you don't have coupling. In fact, you can control K with the quantity of liquid you have in your can, okay? So you have made the whole experiment by drinking Coke. So let's drink some Coke, put it again, let's drink some Coke, and see how it's the synchronization time. This is a homework, okay? So you can do it also with beer, I guess. So at the end, because of the coupling, you have this synchronized solution, okay? So we have passed from this to this, but we have passed not by increasing K, okay? But just letting it evolve because, as I said, they all have the very same frequency, okay? Or very close frequency, and they are coupled very strongly. So already K is very strong. When we want to analyze the synchronization transition, what we do is to pass from a situation in which K is not 0, but is very small, and this is the stationary solution, you see. This is a snapshot of the oscillator in the unit circle. Here the colors denote the natural frequencies here of each oscillator, and as you see, they fill the unit circle because they are not synchronized. And as we increase K, what happens is that some of the oscillators start to get localized into a synchronization cloud, and this cloud gets narrower and narrower and narrower. And just notice that those oscillators that still are not incorporated into the cloud are those with color red and those color violet, are those that have frequencies that are very different from the mean, okay? These are the ones that are incorporated into the cloud for very large values of K, okay? So I can study this system numerically by looking what happened for each value of K, and if I have to compute, because this is just a qualitative description of what's happening here. If I want a quantitative order parameter of the synchronization, what we can do is to follow the phase of each oscillator, construct a phasor, okay, a complex number, which is assigned to each oscillator, sum all the phasors corresponding to each oscillator, take the average, and then you will have another complex number with this modulus and this phase. This is the average phase of the system, and this modulus, okay, will be very large in this case, because all the phasors are pointing to the very same to the very same point, in the very same direction, or this value will be very small in this case because when I sum, the sum is destructive, okay? So a lot of terms cancel out, okay? And what you have is a synchronization, is a modulus of the order parameter, the Kuramoto order parameter, which is very low. And you have this diagram, okay? If you go and study what happened here, what happened here, what happened here, etc., you can measure the value of this modulus and you see what happened. And you see that synchronization emerges when K is large enough. And this is important. Synchronization do not emerge at the very beginning. You need to reach a point in order to make the current state unstable, okay? And this is the synchronization threshold because from this point on, the synchronization cloud starts to form and the synchronization grows because the cloud get more and more oscillator into it and get more and more concentrated around some point, okay? And this is the full synchronization regime. So we have three regimes: the incurrent regime, the synchronization onset in which the cloud start to appear, and the full synchronized state. And we are going to analyze what happened here, okay? No, this is just the order parameter. This is a description, okay? In the equation, the coupling is before the sum of the sinus of the difference. And this is just how I describe the degree of the synchronization, okay? So here you don't find K because it's a descriptor of the system, okay? Okay, let's see. This is the equation again. So this is what you have, and this is how you describe what you have, okay? So K is here. K is small, K very large, and there is some critical point in which this synchronization cloud emerges. Let's see where this synchronization point is. Okay, let's take the original Kuramoto model. This is the Kuramoto order parameter. Let me take the Kuramoto order parameter, and I multiply both sides by this quantity. Okay, I have multiplied, both sides, this side and this side, by this quantity. So I have this, okay? Here is after multiplying this by this, and this is after what happens after multiplying this by this, okay? You see it? Okay. Then this is a complex number, okay? Then take the imaginary part of the complex number. So RT, and this is, you know, cosine plus I sine, so I take the sine, and here is the same. I take all the imaginary parts. Okay, let's look at this, and there is no Homer Simpson here, but you will see that this part resembles a lot to this, okay? So what I can do is to remove the sum here by this expression, okay? Obviously, we have to multiply by K because here is a K missing, so I multiply K here, and what I have is this equation. There is no approximation here, okay? It's just the incorporation into the equation of the Kuramoto order parameter. But the nice thing here is that, as Steven Strogal said, I recommend you to read this article because it's really is one of the the nicest articles you can read about synchronization. When you consider the Kuramoto model in this form, the mean field character of the model becomes evident because you see, what happened is that there are no sum over nodes, over fireflies, over phases oscillators anymore. But what you have is that for each phase oscillator, the evolution of the phase is equal to its natural frequency, obviously, plus a coupling with some kind of inputs, which are a kind of average inputs that come into the Kuramoto order parameter. Remember that the Kuramoto order parameter is just the sum of all the phasors, etc., the modulus, and the average phase of the system, okay? So there are no sum anymore. And for each oscillator, you have the same. Its natural frequency plus a coupling with a mean field, okay, that takes into account all the inputs you have in the system. This is because the reason, and this is a spoiler, I mean, because you have an all-to-all coupling, okay? It's true that each oscillator is different. This is true, and this is here, okay? The thing, sorry, oh. Okay, come back, sorry. So the fingerprint of the heterogeneity in the natural frequencies is already there. Okay, we can review everything. And the fact that this is an all-to-all system, okay, is there in the form of this mean field coupling, okay? Also, what you can do is, since this is the average phase of the system, and as you see, the average phase of the system is something that depends on the initial conditions. So what we can do is to put an initial condition in which the average phase of the system is equal to 0. If the frequency is also 0, because we have decided that the average frequency is 0, what we can is we can drop this average frequency and then work with this other equation, which is equivalent, okay? There is no approximation there. It's just a matter of choosing adequately initial conditions that enables you to get rid of this phase. And this is the important equations for us, okay? Okay, let's analyze it. And we know how to analyze it. Let's look to steady-state solutions. In order to have steady-state solutions, we need that this quantity is equal to 0. If this quantity is equal to 0, what we have is that the natural frequency is equal to this quantity, okay? In other words, the sinus is equal to omega divided by KR, right? But the sinus is limited, is bounded between -1 and 1. So this equation cannot be fulfilled for all the oscillators. Only those oscillators that have a very small natural frequency, in particular, smaller than this quantity, so that omega I divided by KR is always modulus less than 1, will satisfy this equation, okay? So for these oscillators, we have that this equation is fulfilled, and we call them lock oscillators. These are the oscillators that are in the cloud. Those oscillators that are already incorporated in the cloud. But those oscillators for which the modulus of their natural frequency is larger than this, they cannot satisfy the steady-state equation, so they are drifting. They are not synchronized. They are still not synchronized. Look, what can I do in order to incorporate more and more oscillator into the cloud? Increase K. If I increase K, this condition becomes weaker, and more oscillators can fulfill it, okay? If K is very small, then this condition is very straight, and it cannot be fulfilled, okay? Okay, so we have this situation in which we have oscillators that are synchronized for a given K, and for the same K, oscillators that are not synchronized. And we can separate them as a function of their natural frequency, okay? So we have a collection of oscillators. I can say, okay, these oscillators from here to here, have it symmetric, obviously, like this, are synchronized, and from here on and from here on, they are not synchronized for a given K. Okay, let's continue. From this separation, what I can do is to compute the Kuramoto order parameter. Okay, I know how many oscillators, or which are the oscillators that are synchronous, but what is the level of synchronization in the system? Take now the Kuramoto order parameter, and I divide, because the Kuramoto order parameter is just a sum, in two terms. The sum of those oscillators that belong to this group, plus the sum of the rest of the oscillators, okay? Since it's a sum, I just divide the sum in two parts. Why? Because of this. Obviously, for those oscillators that are drifting, they fulfill a situation like this one, okay? So the sum is destructive again. So we have that this contribution, this sum, is equal to 0. So I have to focus on the sum of those oscillators that are locked, or in other words, of those oscillators that fulfill this condition, okay? Then I put the integral, and now the integral does not go from -infinity to +infinity. No, goes from -kr to +kr because correspond to those oscillators that fulfill the locked condition. Obviously weighted by the number or the probability of finding an oscillator with natural frequency omega, and then you can do this integral, okay? Do the integral. This is an integral with two parts, one real, one is imaginary, and we have the real one with the cosine, the imaginary one with the sine. Here the sine, because we are in the condition of drifting, remember that the condition of drifting is omega I divided by kr star, okay? So we can change this sign by this, okay? And since this is an even function and this is an odd function and the interval is symmetric, this is 0, okay? So this integral is equal to 0, and I have only this integral. Okay, let's consider then this integral. Let's make a change of variable. Instead of working in the frequency domain, let's work in the phase domain. So we make the phase change according to the sinus phi star equal to this. And we have this equation. And this equation is the one that fulfills the locket oscillator and is the one that tells you how large is the level of synchronization, is what we are looking for. The problem with this equation is that you cannot solve it directly because it's an implicit equation, okay? Because in order to have to obtain R here, I have to solve this, and we have R here, okay? So it's not straightforward. What we can do many things here, but the easiest way of tackling this, because I want to know what happened here, that is, I want to know what happened when the level of synchronization, the value of R is very, very small, is to consider the limit in which this R is small. Well, sorry, before this, there is a trivial solution here. Okay? You see that if I put R equal to 0, 0 here, 0 here, this is a trivial solution. This solution is the incoherent solution, okay, which is always there, okay? The thing is when this solution have a counterpart, which is the non-trivial solution, which is the synchronized solution, okay? So here we have the trivial solution, okay? I don't mind because I'm not interested in this. So in order to find the non-trivial solution, I can do this because I'm interested in those solutions in which R is not equal to 0, but as I said, I'm interested now in those solutions in which R is not 0, but is very small, so that I can approximate in order to find this value. And when I put R equal to 0, I put here a 0. Okay, so I put here a 0. Obviously, K is not K anymore. Now it's Kc, which is the value close to the synchronization onset, because this equation is only valid when K is equal to Kc. And if you solve this equation, this integral, which is really, really simple, you can do it in many, many ways, what you find is this. You find this relation for the critical coupling, okay? That tells you that the critical coupling is 2 divided by P and this G0, which is the number of oscillators that, from the very beginning, are already pacing, have a natural frequency which is already the mean one. In other words, those oscillators that are synchronized already in the uncoupled limit. If you have a population of oscillators in which this is very large, meaning that you have a very peak distribution, okay, G omega, then what happens is that the synchronization coupling, the critical coupling, is very small. But if you have a very broad distribution, okay, in which this value is very small, what happens is that this value is very large. You need to go to large critical couplings in order to observe the emergence of the synchronization cloud. Okay? Any question? Okay, so now is the time for the dessert, but as I promised, and I think we are on time, I finish now so we can have 1 hour and a half. And tomorrow we will start the lesson with this continuous formulation, which is again, a solution of the Kuramoto model, but using another strategy, which is totally different, okay? But it's very useful if you, and maybe for you, it's convenient to know because you can find it in many papers about synchronization, not only in the Kuramoto model, but in many other nonlinear models, okay? Okay, so if you have a question, yes. Yes.
But qualitatively, I really do need to consider that because, I mean, if I assume that I have enough elements, if I consider that I have enough number of elements that are connected, qualitatively, those really make difference to have a big number or full number?
No, in this situation, I mean, it would be the same, okay? The things are totally different, and we will see tomorrow when the typical connectivity is much smaller than the number of oscillators, okay? This situation is very different because in this case, you can talk about averages around nodes, but these averages are not so rigorous, okay? Because for talking that you, as a node C, and mean field, you need that the number of neighbors you have is very large. So in a situation in which you don't have a strictly an all-to-all coupling, but the coupling on all the nodes or almost all the nodes is very large, okay, then the mathematics would be the same. I mean, you will make approximations, but these approximations will be, I mean, will be good, okay?
More questions?
Thank you very much.
Thank you.
I want to know, your presentation asks about the synchronization of frequencies, all complete synchronization. I want to know if your presentation talk about the synchronization of frequencies only or complete synchronization.
When you focus on the full synchronization regime, you mean? Okay. Yes. Okay. In this case, what you have is phase synchronization. Okay, you have phase synchronization. Yeah, because all the phases go to the well. The thing is that the problem is that the cloud, when you go and do numerics, etc., you see that the cloud have a width, okay? Because obviously to achieve the full synchronized regime, you will need to go to extremely large scale. But in principle, it's phase synchronization.
More questions? No? Okay, so let's thank
you very much.
Thank you. So remember, we have to be back by 2 o'clock, right? The clock is at 2.